Welcome to Pre-Calculus Sequences and Series. In this video, we are going to investigate infinite geometric series. So in the previous video I hope you watched was over finite geometric series, and that's where we say, hey, we got a geometric series here, and we want to add together the first 25 terms, or maybe we want to add together the first 10 terms, or maybe we want to go crazy and add together the first 300 terms, but those are finite, right? When you have a set number of terms, that is finite. But there are some very specific situations where you could actually add together an infinite series, which infinite means forever. So you're going to take a sequence and you're going to add together all of the terms from the first all the way to the infinite, which sounds really impossible. But let's investigate. So here's exactly what I'm talking about. All sequences that are not finite are infinite. So you could be asked to find the sum of an infinite sequence, which would be called an infinite series. Remember, a series is just a set of numbers from a sequence that we add together. But if that set of numbers is infinite, well, that's an infinite series. And we could represent this using our sigma or summation notation. So we have that sigma there for the sum, and we're going to say, hey, let's start at the first term, and let's go all the way to the infinite term, and that just sounds impossible. So that would literally be adding together the first term, the second term, the third term, the fourth term, dot, 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 dot. And that's really difficult. So let's talk about how we could actually make this happen. So first off, arithmetic sequences have no infinite sums. It's just impossible. So if you're an arithmetic sequence, whether you're going up or you're going down, remember arithmetic sequences go up or down forever, so there's no end in sight. So it would be impossible to add together all of the terms. So if it's arithmetic, you don't have to worry about this. But if it's geometric, you can possibly. So here's the deal. If you have a geometric sequence and the R value is greater than 1, then there is no such thing as an infinite sum. You know, if your R value is 2, that means you're multiplying by 2. So 7 times 2 is 14. 14 times 2 is 28. 28 times 2 is 56. Again, so if you're multiplying by a number bigger than 1, you're just going to keep getting bigger and bigger and bigger. And there's no way you can add up all of those infinite numbers because they're just going to keep getting bigger and bigger and bigger. Again, they're diverging, right? Diverging means that there's no end in sight. You're just getting bigger and bigger and bigger, even if that's in a negative direction. So all arithmetic sequences are divergent, and geometric sequences with an R value greater than 1 are also divergent, so there is no infinite sum. But if you have a geometric sequence where the absolute value of your R value is less than 1, then you can have an infinite sum. So again, your R value, the absolute value of your R value, has to be less than 1. If that is true, an infinite sum is possible. And I don't know if you remember this or not, but a couple of videos ago, when we were talking about series, we looked at an example where we basically had 3 tenths plus 3 hundredths plus 3 thousandths. And basically it was 0.3 plus 0.03 plus 0.003. And every time we added a new term, it was just adding a 3 to the end of that decimal. So we recognized that, oh, that's just going to be 0.3333333, which is 1/3. That was an infinite series. And again, the R value there was less than 1. So let's take a look at the formula for this, because the formula is absolutely unbelievably easy. So if you have that geometric sequence with an R value less than 1, can't emphasize that enough, the R value right here has got to be less than 1, it will converge onto a specific number. And to find that number, the formula, the formula is actually easier than a finite series. It's funny to me, right? Like you would think the formula for an infinite would be weirder or harder. It's actually easier. It's unbelievably easy. All you do is take the first term you care about. It's typically the first term, but remember, not always. It's whatever term they tell you to start with. So the first term you care about goes on top, and you divide by 1 minus your ratio. That's it. That's the formula. That's how simple it is. That's the formula for the infinite geometric series. Very, 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 very easy. All right, let's put to use some examples here. All right, so this first example wants us to add up all terms starting at 1 and going all the way towards infinity of this geometric series or sequence. How do I recognize that this is geometric? I can't emphasize enough. If your variable is in the exponent, you are guaranteed to be geometric. Now, can I actually go ahead and find this sum? Well, since my R value is 0.75. Actually, you do the absolute value of r, but it's positive. So the absolute value of r is 0.75, which is clearly less than 1. So yes, this series will converge onto a specific number. So all I got to do is take the first term I care about. The first term I care about is found by plugging in 1. 1 minus 1 is 0. 0.75 to the 0 is 1. 1 times 3 is 3. So there's the first term I care about. And then this is so easy. The denominator is just 1 minus that common ratio, 0.75. So when you go to your calculator, this is so easy to type in. 3 divided by... Now, you could do the denominator in your head, or if you do want to type it in exactly as you see it, please, I'm begging you, you have to use parentheses. But again, you could do that in your head. 1 minus 0.75 is 0.25. So you could do 3 divided by 0.25 as well, and you would get the same answer, 12. So if I were to continue to add these together over and over and over again, the infinite sum would be 12. And the idea of this, guys, is this, when your r value is less than 1, you should have learned back in algebra that you are a decay function. So basically your values are getting lower and lower and lower and lower and lower. So values way over here, I mean, for example, what's the millionth value? I mean, there is a millionth value to this, but the problem is it's decaying so much that the millionth value is really just like dust. It's like as close to 0 as you could get, and that's why it just doesn't really matter. So that's why we do end up getting a number that we converge upon, and that is 12. All right, let's take a look at this next one here. A little bit different, but again, the variable is in the exponent. So yep, this is a geometric sequence. Now, can I find this infinite sum? Well, the absolute value of negative 4/5 is positive 4/5, which is definitely less than 1. 4/5 is less than 1. So yes, I can. All right, so the formula is very easy. Again, what's the first term? Watch out. Here I'm starting with the 0th term. So for this problem, the first term I care about is actually found by plugging in 0. And that's simple. Negative 4/5 to the 0 is 1. And then the denominator, I'm going to do 1 minus, but be careful because my ratio is negative. It's going to be 1 minus negative 4/5, which obviously is going to be 1 plus 4/5. Now, you could just go to your calculator, or you could just kind of do this on your own, right? We're smart math students. 1 is 5/5. So on the denominator, 5/5 plus 4/5 is 9/5. And 1 divided by 9/5 is going to be 1 times the reciprocal, 5/9. So there's my answer, 5/9. But again, don't be afraid. You could definitely grab your calculator. Just be careful. 1 divided by, in parentheses, 1 plus, need another set of parentheses for that fraction, 4/5. And then I got my answer. And again, change that to a fraction, 5/9. But this one's pretty good that I think you guys should be able to do the algebra on that one. All right, let's try this next one here. All right, so once again, this is geometric because the variable is in the exponent, but they do want me to find the infinite sum. But I can only find infinite sums if my r value is less than 1. So it's the absolute value of my r value. The absolute value of 7/5 is 7/5. But wait a minute, 7/5 is greater than 1. So this has no solutions. There is no infinite sum here because my r value is greater than 1. If your r value is greater than 1, you're getting bigger, not smaller. So you're diverging, not converging. Now, a lot of kids think that all fractions are less than 1. Okay, let's not be in 3rd grade. If your numerator is bigger than the denominator, you're bigger than 1. So instantly I can tell that this is a diverging series, not a converging one, so I cannot find the infinite sum. How simple is that? All right, let's just do one more example. This time I'm not giving you that summation notation. And that's where we say, well, hey, let's write it, right? So first they want me to find the sum. This must be the first term. And the dots imply that they want me to keep adding forever towards infinity. So let's see. Now what I'm going to do is I want to find my geometric formula, right? So again, the geometric formula is the first term, 1, times the common ratio raised to the n minus 1. So what the heck's my common ratio? Well, what's happening here is I'm multiplying by 1/2. 1 times a half is a half. 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. 1/8 times 1/2 is 1/16. And then 1/32. And then 1/64. So my common ratio is 1/2. So there's my formula, 1 times 1/2 raised to the n minus 1. So again, I was able to use the series to create the summation. That's a big skill you need to be able to do. So again, the dot told me it's going to infinity, and then I found my formula. All right, this is clearly a converging series. And again, first off, I see that the values are getting smaller and smaller and smaller. I also recognize my R value is clearly less than 1, or less than 1, sorry. It is a half, which is less than 1. So that means I can find this infinite summation. All right, the formula is to find the first term. The first term I care about is the first term. I could look right here to get it, or I could plug in 1. 1 minus 1 is 0. 1 half to the 0 is 1. 1 times 1 is 1. Either way, the first term I care about is 1. And the denominator is 1 minus a half. All right, now I can do this by hand again. That's 1 minus a half is a half. And that's going to be 1 times the reciprocal, which is 2. So I get 2. All right, and this actually makes sense, right? Like the first term is 1, and then if I add 0.5, now I'm at 1.5. And then I'm going to add 0.25, so now I'm at 1.75. And then again, the number I add keeps getting smaller and smaller and smaller. So yes, I continue to add forever, but the numbers I'm adding are so small that they barely make a difference. So it's actually important to realize that you're never, ever, ever going to get to 2, right? Because you do keep adding, right? Even though it's infinite, even though the numbers are converging, you're still adding, right? So you're never going to get to 2. You're just going to get really, really close that you might as well be 2, right? And we actually saw this in the past with horizontal asymptotes, right? It's the idea that, you're going to get closer and closer and closer to that horizontal asymptote as you go more and more and more towards infinity, but you're never going to actually get there. But the answer to this problem is 2. Hopefully you found this stuff pretty easy. I think infinite series are actually super easy because the formula is really, really simple. You just got to be careful that you don't get tricked. You can only do it if your R value, the absolute value of your R value, is less than 1. All right, guys, that's it. Hope you enjoyed.